Welcome to our tutorial on finite element analysis with ANSYS workbench. In this video, we'll guide you step by step through the process of analyzing a beam structure from pre-analysis to the final results. We will cover important concepts such as governing equations and analytical solutions and show you how to create and measure the geometry, set up the physics and interpret the results. Whether you are a student, an engineer or just curious about FEA, this tutorial will give you a solid foundation in ANSYS workbench and beam analysis. So let's get started. Now let's take a closer look at this problem we'll be simulating in this video. We have a cantilever beam with a length of 5 meters, a width of 0.6 meters and a height of 0.6 meters. The beam is clamped on the left side and has a uniformly distributed load of 10 kilonewtons per meter acting on the right side. The material of the beam is structural steel with a Young's modulus of 200,000 MPa. This case study will give us a better understanding of behavior of beams under uniform loading conditions and help us design more efficient and effective structures. The finite element process is a series of steps we take to analyze a structure's behavior. These steps include pre-analysis, geometry, match, physics setup, numerical solution, numerical results, verification and validation. Each step is important to understand the concepts and obtain accurate results. Let's take a brief look at each step. Before we dive into the ANSYS simulation, it is important to establish a solid foundation for our analysis. This is where pre-analysis comes in. In this section, we'll explore the fundamental theories of beams and their governing equation in ANSYS. We'll also cover the analytical solution for our problem statement. So let's start building our knowledge from the ground up. Now that we have our problem statement and gone through the finite element process, let's take a closer look at the governing equations that will be used in our ANSYS simulation. In ANSYS simulations, we use governing equations to describe the behavior of a beam under different loading conditions. Two governing equations are used in ANSYS. The Euler-Bernoulli beam theory, which assumes that the beam is slender and the cross-section of the beam is not distorted during deformation. This theory is suitable for beams with a high length to thickness ratio and small transverse deflections. The Timoshenko beam theory, which considers the shear deformation of the beam and is more appropriate for beams with low length to thickness ratios and large transverse deflections. These are the main theories that are used in ANSYS workbench. Differences are shown in this table between both the theories. Also the element type through which ANSYS recognizes each case. Before we jump into the ANSYS simulation, let's first discuss the analytical solutions for our cantilever beam problem. In this section, we will perform hand-based calculations to determine the deflection and stress of the beam under the applied load. This will serve as the benchmark for our ANSYS simulation results. Here is the given data for our cantilever beam problem statement. Our objective is to find the maximum reaction force, maximum bending moment, maximum deflection, maximum bending stress, and the shear force diagrams for the cantilever beam under the applied load. Here are the formulas which we will use to calculate the maximum deflection and maximum stress of the cantilever beam. The deflection formula takes into account the material properties of the beam and the applied load, whereas the stress formula considers the bending moment and the cross-sectional properties of the beam. Now that we have completed the hand-based calculations, let's take a look at the results. The calculated values for inertia, maximum reaction force, maximum moment, maximum deflection and maximum bending stress are displayed on the screen. The shear force diagrams provides us with a visual representation of the beam's response to the load. As you see, the maximum shear force occurs at the fixed end of the beam, while the maximum bending moment occurs at the location of the point load. These results are critical for ensuring the safety and performance of the beam under the given loading conditions. Let's move to the next section, where we will be using ANSYS workbench to simulate the behavior of the beam. Now let's move on to the geometry section for our analysis. This step involves defining the shape and dimensions of the beam we are analyzing. The first step in geometry section is to sketch the midline of the beam. This is done to define the shape of the beam. Let's move to ANSYS. We have moved into the ANSYS workbench, where we will be creating the basic geometry line. So first of all, in the ANSYS workbench, save your project at your desired location. I am saving it on my desktop. After saving your ANSYS workbench file, see Analysis Systems. From the Analysis Systems, click on Static Structural. Now drag this static structural system into the project schematic and create a standalone system. Now we will be creating a basic line. So right click on the geometry and go to new design modeler geometry. The bottom shows a red blinking light starting the design modeler, which means our design modeler is being opened. Now we have loaded our design modeler, where we will be sketching a line body. So click on XY plane, then look at, make sure your units are in meter. Then from the tree outline, go to sketching and then select a line. From the origin, create a horizontal line which shows H as the constraint. Create the line, give it some dimensions such as horizontal dimensions, or click on the vertical line and click on the point, the end point of the line to give the dimension. Give the dimension and give dimension as 5 meters. Now come back to modeling and select the sketch that you have created. Now from the concept, select lines from sketches. This will create a line body for our geometry, because we are doing a 1D simulation. Now the next step is to specify the moment of inertia, which is the measure of beam's resistance to bending. Let's again go to the ANSYS workbench to create the geometry. So we are again back in the design modeler. Now we will create a cross section. Now to create a cross section, go to concept, then cross section. Now as we have a rectangular cross section, we'll create a rectangular cross section. Now give the breadth and height as 0.6 meter and height is also 0.6 meter. Now here you can see in the physical properties, the inertia is given as 0.0108 meter power 4, which means that our calculations were right about the inertia. So we have created a line body and the cross section. Time to apply the cross section to the line body. Now from the tree outline, apply line body, select line body. Now in the cross section, select the rectangle 1 cross section for the line body. Now what happens that the cross section has been applied to the line body, and we can see that by going to view and display cross section solids. So our inertia has been applied to the line body. Meshing stage, we create a mesh or a grid of small elements. that make up geometry. This step is crucial in the finite element analysis process as it creates a discretized model of the geometry. The two main steps in the meshing are creating the mesh and calculating the degree of freedom at each node. The degree of freedom determines how many results ANSYS will calculate at each node. Let's go to ANSYS workbench to create the mesh. As we have created the line body and have given the cross section to the line body, we'll close the design modeler and open up the workbench and double click on the model. ANSYS mechanical will start to load. You can see that the ANSYS mechanical is loaded. We'll create the mesh for the body. Click on mesh, then right click on it and insert sizing. To select the geometry, click on geometry first, then select from edge and then select the edge or the line body and apply. Now in the type, select number of divisions. Now the number of divisions tell you that in how many divisions the body will be distributed, which plays an important role in the results. I am going to divide it into 6 or 10 divisions. I am going to divide it into 10 divisions. Now let's minimize this and open ANSYS workbench. Now you can see that there is engineering data over here. We can double click over here. Now we can change the material, but as we only need structural steel over here, so we will let it be structural steel. Let's see that our Young's modulus is right or not. So you can see that here is Young's modulus, which is 2e into the 11, which means 2 with 11 zeros. So it is equal to 200,000 MPa. So our Young's modulus is right, and the Poisson ratio is also right as in our problem statement. Now let's go to our mechanical ANSYS mechanical and specify the boundary conditions. Now as we have a cantilever beam, its one end will be fixed. Click on static structural first and then right click on it, insert fixed support. Now we want only one point to be fixed, so we will select point vertex from here and select one point and apply fixed support on it. Now we have to give an uniformly distributed load over here. Now the ANSYS equivalent to uniformly distributed load is the line pressure. We'll select this line and apply. Now our line pressure has been applied to this, but we haven't described the magnitude. So from details of line pressure, we'll add components, and as it is in the negative y direction, so we will add negative 10,000 force. So the line pressure will be negative 10,000. You can also see the force metric over here, that this is negative 10,000. This is from the origin in the negative y direction. We have added our boundary conditions mechanical. We can get our solution by solving it. Now I will go into the solution information and then control F, and then I will select element type. Now it says that element 1 is beam 188. Now we have discussed that beam 188 is Euler beam theory. So further information is displayed on the screen regarding beam 188 and what is beam 188. So our solution has been done. Get the plot of deformed of the midline, the plot blending, and we have to plot bending moment. Also we need the shear force moment diagram along the line. So to get the results, first we click on solution, right click on it, we say we want total deformation. Let's solve it. Now it shows us the total deformation that has been caused. Now click on solution, right click and add the beam tool. Now we have added the beam tool. Now insert the bending stress from the beam tool, adding the maximum bending stress from the beam tool. Also we will add deformation from the beam tool as well, total deformation. Now let's solve it. Now we can see that these are our results of the beam. If you want, you can also see it into thick shells and beams, through which you can see a 3D type result. But remember that this is 1D simulation. Now we can see that our result is 0.36826. So we need to add the bending moments as well. So go into solution, insert beam results and add the bending moment. Now for the bending moment we will require a path to be described. Now click on model A4, click on construction geometry and add a path. Now the path type should be edge. Select edge and now from the above selection method, select edge and click on this edge. Geometry, apply. Now a path has been created in this line body. Now let's go to the solution, the bending moment. Geometry selection, or we can go for path selection. On the path of our path, we should give it the bending moment along our path. We'll also add our shear moment diagram and describe the path in the required. We'll also add our shear force diagram and add path and select our path. Let's solve it and see our results. Now there is a random error which says that our shear model may contain many internal nodes, but as we are only doing 1D, so we do not have, so we can neglect this error. Now this is the maximum combined stress that has been. You can also play this animation by clicking on play, which shows that our maximum combined stress is at the fixed edge of the beam. We'll also see the total deformation. That the major deformation is done in the red area, which is the tip of the beam or the right end of the beam. Total bending moment. Now it will show us the total bending moment along the beam. So I'll click on this view, and this is the bending moment diagram for our result. Now it is similar to what we concluded. Now let's see the shear moment diagram. Now this is the shear moment diagram. This is our shear force diagram. So we have added some results to our numerical solution that we created. All for the numerical results. Now let's proceed to the next step. The next step is verification and validation, which is most important in the ANSYS workbench study. Let's check our results with the analytical results to see that whether our results are okay or not. So I'll open the results from the PowerPoint presentation so that we can compare. So here are the results. So we'll have to see the maximum reaction force, which is 5000 Newton that we calculated. So by the force reaction, there is 5000 Newton reaction. So our first result is verified. Now the second is maximum moment, which is 125,000 Newton meter square. Now let's go to our moment. Maximum total bending moment. Now the maximum moment is 125 into e to the power 5 maximum, which is in Newton meter, which is also satisfied. Now let's see our maximum deflection. Now this is 0.00036169. Now let's see our total deformation, and which is 0.00036826. Now remember that this is an approximation. These are the results which are through approximation and should not be considered as the perfect results. These are only approximate results which can vary with the experimental and analytical results. So this is also correct. So our results do match our solution, which means that our solution is right and correct. So we have completed our ANSYS simulation.